Hello, my name is Jordan Burton, and I'll be presenting Protstatmd, a NextFlow containerized analysis pipeline for spectral count proteomic analysis, which doubles the number of pairwise comparisons between beer samples. In early 2020, the ABRF Proteomics Research Group sent out a logger for labs to analyze via mass spectrometry. And so they asked us to identify and digest our own beers to add to the study. And so I had a bourbon barrel aged beer and an imperial farmhouse ale that I brewed, and I digested all three beers and ran them on a fusion tribrid with an MPLC in data-dependent acquisition mode on a 60-minute gradient. Once I had the raw files, I uploaded them to the Wayne State high-performance computing grid and used NextFlow, a command line tool which links containers with scripts and computing environments for raw file conversion, database searching using the MSGF or Comet algorithm, false discovery rate correction using the percolator algorithm, and statistical analysis. In the default NextFlow environment, the statistical analysis is using MSstats for area under the curve analysis. In Protstatmd, we use EdgeR to compute the statistical analysis using peptide spectral counts. All of this is done in one line of code. When comparing the number of proteins quantified for Comet or MSGF and MSstats with Comet or MSGF with EdgeR, we see that EdgeR doubles the number of proteins quantified in all beer samples. And this is likely because spectral count data allowed more proteins to be quantified, as many proteins were missing area under the curve data. MSstats is incorporated into the default proteomics NextFlow pipeline to identify differentially abundant proteins using area under the curve values. And we can see here that the greatest number of differentially abundant proteins were from yeast, followed by barley and wheat. With our Protstatmd container, using peptide spectral counts to make pairwise comparisons, I want to note that the y-axis has changed from 100 to 250 at the top. And we see that the same species, yeast, barley, and wheat, have a great number of differentially abundant proteins, but these are higher than when using area under the curve data. The Protstatmd NextFlow pipeline exports p-value histograms to allow the user to validate the number of differentially abundant proteins identified. The distribution of p-values in all of these comparisons for yeast or barley is skewed to the right, and this is expected because these three different styles of beer are expected to have many differentially abundant proteins due to differences in brewing conditions and fermentation. Protstatmd also exports interactive volcano plots that the user can use to inspect the differentially abundant proteins and identify proteins of interest. We see here that there are many more differentially abundant proteins for yeast in all three comparisons than non-differentially abundant proteins, while with barley, the number of differentially abundant proteins is somewhat similar or less than the number of non-differentially abundant proteins. And this is likely because barley was used in all brewing processes. In conclusion, using peptide spectral counts doubles the number of quantified proteins compared to area under the curve, which allows more pairwise comparisons to be made between beer samples. And finally, Protstatmd exports data into HTML files, which can be found by scanning this QR code. And these HTML files, again, are interactive. Finally, I would like to acknowledge the STEMR Group and Proteomics Core Facility, the NIH, Wayne State University for funding, and Wayne State University's High Performance Computing Grid. Thank you.